Hello and welcome. This is the second lecture on the Crystalline Silicon Solar Cells lecture series. Again, I'm Edward LeBeau, electrical engineering student here at Arizona State University. So let's dive in. This lecture we're going to be talking about the operation of silicon solar cells. So light shines, sun happens, energy comes out, what's going on? So we're going to begin to answer those questions. Before we dive in, we're going to do a joke of the day. I'm a student too, so I know what it's like to sit and lecture and begin to fall asleep. So let's kick things off with the joke of the day. Hopefully this will keep your attention. So, why did the sun go to school? To get brighter. That's a knee slapper. Alright, hopefully you'll be able to tell better jokes than me by the end of this. So let's quick run through our outline. First thing we're going to talk about is operation. So sun shines, energy comes out. What's a little bit of what's going on there? Then we're going to look in more particularly into the generation. Then we'll look into band gaps, losses, lifetime, and the IV curve. So don't worry, you probably don't understand all those things yet, but we'll touch upon all of them by the end of this. So here we go, solar cell operation. So the sun shines, it hits the solar cell, electron hole pair is generated, energy comes out. What's going on? So the best way to understand it, let's think of it like a light bulb. A light bulb, you apply current and voltage. You apply voltage, that creates a current. The light shines. It's the inverse of that. This time, a light shines onto the solar cell. It creates a current and a voltage, and then energy comes out. So the basic understanding is the opposite of a light bulb. Just think of it like that, opposite of a light bulb. So what's going on here? So generation. So the light shines, it hits the solar cell, and a thing called generation occurs. You generate an electron hole pair. So basically the things needed for generation is you need an electron in the valence band. And there's ways to get a lot of electrons in the valence band. We'll talk about that. That's doping. We'll talk about that shortly. You need an empty state in the conduction band, and then you need a photon with enough energy to jump that gap. So if you look at the graph on the right, you see EV and EC. There's a gap between the two. That's called the band gap. Generally for solar cells, I want to say it's 1.1 EV to jump that gap. So if the photon doesn't have enough energy to do that, it does what the electron on the far left of that graph does, is it jumps about a chunk of the way and then just comes right back down. Or the electron on the far right, where it jumps way too far, well, it's still in the conduction band, so you can still retrieve some of that energy, but all the excess energy comes off as heat, which is a thermalization. It cools down. That releases photons, and sometimes even that releases phonons, and sometimes even that'll put out a photon every now and then. So now, what I was talking about before, there has to be an electron in the valence band. So that's called a free carrier. A free carrier is an electron in the material that can move about semi-freely. So the way you do that is you dope it. So the way to do this is to create an N-type material. You take silicon and you dope it with a group 5 atom. This creates an extra electron because a group 5 atom, remember, has the 5 electrons, whereas silicon has the 4 electrons for bonding. So that creates an extra atom. Or if you want to do a P-type silicon, you dope it with a group 3 type atom. And again, so now you have silicon, which has 4 bonding electrons, and then you have a group 3 type atom, which has 3 bonding electrons, which then you have an extra hole. So there's a missing electron there, right? So that's free carriers. Again, all the free carriers are waiting in the valence band to get hit by photons and jump to the conduction band and create energy, power our homes, all those good things. So the next thing to look at is, briefly, we're not going to go in great depth on direct and indirect band gaps because that's a very quantum mechanics intensive discussion. But if you look at it, on the right you have the far right graph, not the left graph. You have your conduction band and your valence band, and this is silicon. And if you look at it, your x-axis is your momentum, and your y-axis is your energy. The way you put momentum into the system is phonons, which could be thought of as a vibration or something like that. And the way you put energy into it is photons. So if you look at it, the shortest bridge between the valence and the conduction band, least amount of energy required, is not directly above the valence band. You'd have to come to the right some of the ways. So the chances of you going to the right are slim, because that means an electron has to, or the silicon has to absorb both a photon and a phonon at the same time. So an electron has to be excited by a photon and a phonon at the same time. The likelihood of that happening is slim, which means the electron then has to jump that bigger gap. So this is the reason why there's not as great of absorption in silicon, and also another reason why it wouldn't make a very good flashlight, right? Because of all the different issues with momentum and phonons. So the next thing to look at is absorption coefficient. So the absorption coefficient tells us how far into a material light will penetrate before it's absorbed. So this is important to know when you're designing solar cells and all those things, determining how thick you want your photovoltaic cell to be, because if it's too thin, right, then it'll appear to be translucent, light will just shine straight through it, it won't be absorbed. But a big thing to note on this graph that we're going to highlight right here is silicon is the red line. And a little bit past 600 nanometers, maybe 700, just that sharp falling off of the absorption. So the reason why that's happening is longer wavelength light have lower energy. So when we're getting above 600-700 nanometers, we're exiting the amount of minimum energy needed to jump the band gap. So then we can't absorb those lights anymore. And also another thing to note on this graph is the high energy lights are absorbed, if you look at it, 10 to the 6, so further into the cell than the lower energy lights. Lower energy lights are absorbed more towards the front of the cell. So then the next thing to look at is the generation rate. So the generation rate is the cell depth, how deep into the cell, and how many electrons, or how many electrons are jumping to the conduction band in that area. So if you look at it, towards the front of the cell, you have your highest generation rate, which means that's where most of your electrons are in the conduction band, is towards the front of the silicon. And then towards the back, it's less and less and less, right? So the thing to note there, which is good, because you collect your energy at the front. You don't collect it towards the back, right? You put your metal on the front, and also metal on the back, but that's way further back. So it's good that they're right up front, but sometimes that isn't so good, because then you get two electrons in the conduction band that start to interact with each other and sometimes give their energy to another electron or run into each other, things like that, and that'll cause some losses. And now that we're on the subject of losses, a big reason for that is impurity in silicon. Some of this impurity is intentional. Remember, we were talking about dopants. We need those free carriers, but also it'll cause some issues. That it comes with a price. It'll create, if you look at that, this is an energy band diagram, and all these other little atoms and elements are written on it, and you don't have to know all those or anything like that, but those create different discrete energy levels within the silicon, and those energy levels are not the conduction band. So they'll detract, so an electron will maybe jump from the valence band to one of those discrete energy levels, which is not a collectible energy state for us. So it can cause some issues. So again, your doping comes with a price, and especially other impurities in silicon that haven't been removed come with a hefty price with no reward. Unlike doping, where there is a reward, where you get more valence electrons, more free electrons. So now that we're talking about that, we're going to look into recombination. So recombination, there's three major types. There's radiative, Shockley-Reed Hall, and Auger, or Auger, as some would say. Radiative is the one on the left. Is basically your electron jumps to the conduction band and it just takes too long for it to get collected, so it falls back down to the valence band, and maybe that releases a photon or phonons or things like that. The other thing is Shockley-Reed Hall. Shockley-Reed Hall is from all of those impurities and things like that. It's that discrete energy level between the conduction band and valence band that isn't an area where we can collect energy. So basically, an electron will jump to the that discrete energy level, not on the conduction band, and then come right back down, or an electron will be in the conduction band, it'll jump down to that middle level and then fall back down in the valence band. And again, the driving force there is impurities. Auger or Auger recombination is when there's two electrons in the conduction band, and one electron gives its energy to the other electron, shoots back down to the valence band, and then that first electron shoots up in the conduction band and then just thermalizes right back down. So again, a big energy loss. So those are our three major types of recombination, and those are a big way to define why our efficiency in our solar cells is not 100%. Another thing to note is at the surface of crystalline solar cells, there's a bunch of dangling bonds, and that introduce more defect levels. So just like impurities introduce a bunch of defect energy levels between the conduction band and the valence band, so do dangling bonds. And that, again, will increase the SRH, Shockley-Reed-Hall recombination, which obviously reduces our efficiency, reduces our lifetime, and makes our excited electrons less easy to collect. So, like what I mentioned a second ago, lifetime. So what is lifetime? Lifetime is the amount of time that an electron, or an excited electron or excited hole, can move around before it recombines. It's an average. Obviously some last longer than others, but this is just an average of about how long, when a photon hits a solar cell, electron-hole pair is generated, about how long do they stay apart before they recombine. That's your lifetime. And a big thing to think about there is the recombination rate. So the recombination rate defines how many recombinations you have per second per unit area. So obviously a high lifetime, low recombination rate, right? Just like that. They're inversely proportional. The best way to think about lifetime is just the average time an excess electron can spend in an excited state before it recombines. Just an average time before recombination. So obviously if you have a very high lifetime, the chances of collecting it are very high. If you have a very, higher than if you had a very low lifetime. Now the next thing to think about, very much related to lifetime, is your diffusion length. So your diffusion length is how far can it travel. So this is very important when you're determining on your front contacts how much space you want. You know, if your space between front contacts is this much and your diffusion length is this, well, you're not going to collect a lot of your free electrons or your excited electrons. They're just going to recombine because their diffusion length is shorter than that. So just like lifetime, it's an average, and very similar to lifetime. You can think of it very similar to lifetime, just opposed to units of seconds or time, it's units of distance. And the effective lifetime is just taking into account all the different types of recombination, Auger, Shockley-Reed-Hall, and radiative, taking the inverse of them, and then that's your effective lifetime. So 1 over radiative plus 1 over Shockley-Reed-Hall plus 1 over Auger equals 1 over your effective lifetime. You invert that, and now you have your effective lifetime. So this results in what we would call an IV curve. So all these things are happening. And a big way you measure your success of building your solar cells, you generate an IV curve. And if you look at it, the y-axis is your current, the x-axis is your voltage. So the first thing you test in your IV curve is your short circuit current, which is basically your maximum current your cell can produce, and then you check your open circuit voltage, which is your maximum voltage. So the thing to note is power is current times voltage. So your maximum power point is that dot on the right, upper right corner of the graph. And then inside there, that purple area is your form factor, FF. Your form factor is your maximum current times your maximum voltage over the total area, right? So the total area of that graph is all of that area, and then it's that dark pink over the light pink. Is basically the way to think of it. Higher form factor is a higher power, right? You can produce more energy, so you want a high form factor. So short circuit current, like we mentioned before, is the maximum current produced by a solar cell. So the big things that determine that are the area. So obviously your current is your current density times your area. It also is largely determined by the light that is hitting the solar cell, so the spectrum, and the intensity that the light is hitting it with. It also is determined by your absorption, so how deep into the cell it's absorbed, all those things, and then also is largely determined by your collection probability, which is dependent upon your lifetime and your diffusion length. So all those things go into your short circuit current, and you want a high short circuit current just like you want a high open circuit voltage, so that way you can have a high power output. So if you really want to get your short circuit current up, you need to reduce reflection. So The more light that's reflected by your solar cell is not absorbed. So if it hits the solar cell and bounces off, well, it's not absorbed. The energy is not contained in the solar cell and is not producing electron hole pairs. Another thing is you need to reduce shading. Obvious, very simple thought there, right? If I put my solar cell under a tree where the sun can't hit it, I'm not going to get much energy out of it. Not going to get a high short circuit current. But another thing is, if you have all your fingers, all your bus bars on the front of your solar cell, all those metal contacts on the front of the solar cell, if those are really big, everything under them is shaded. So you have to be very prudent and figure out what's my appropriate front contacts to have minimum shading, but also collect as many electron hole pairs as possible. The other thing is you increase absorption, and then you reduce recombination. So increasing absorption is a little bit more complicated, but reducing recombination is finding that appropriate doping density, all those things. Excuse me. Excuse me. Finding the appropriate doping density, all those things, and then getting rid of all your impurities. So that's the first part of our crystalline silicon solar cell operation lecture. And I'll be back shortly to go more in depth. Hope you guys have a great day. See you soon.